to be going over a wedge problem, working on how to do our calculations for that. The problem states that we have a hydraulic powered log splitter used to split logs in half. The wedge provided the cutting action. The shape of the wedge is an isosceles triangle that is 4 inches thick by 8 inches wide. An actual effort force of 500 pounds is required to split the log in two. Cutting action of the wedge is 90% efficient. Answer the following. So first off, we've got two possible scenarios here when we're talking about our wedge that we could use. The one is a scenario that I think we're talking about, where this is 8 inches and this is 4 inches, going in that way. The other scenario, because at this point I'm kind of confused by the terminology here that's being asked in this question, that it's 4 inches thick by 8 inches wide. The other possibility would be to have your 8 inches here and your 4 inches down here, like this. So we're not exactly sure yet, but let's go ahead. We're going to make the assumption that this here is what we are looking at with this particular. So, and we're going to say, what is the slope length of the side of the wedge? Well, we have ways to do this. If you recall from math class, Pythagorean theorem is a squared plus b squared equals c squared. And I can form this. We have to have a special condition in order to use that. And that is, we have to have a right angle, or a right triangle. Well, in this case, we do not have a right triangle here, but I can force a right triangle. I can bisect this triangle and force a right triangle on half of this wedge. And that would give me, we will label this as A, this is B, and this is C. Our hypotenuse is always going to be C. So if I take A squared plus B squared equals C squared, well, the size, notice we had 4 inches overall. Well, if we've bisected that, A becomes 2, so 2 squared plus, which is 8 squared, equals C squared. So 4 plus 64 equals C squared. So this becomes 68 equals the C squared. We got to take the square root of both. So C equals the square root of 68, which will equal, let me get my calculator out here, and we will real quick find out that the square root of 68, I think 68, is 8.246. 8.246. Go ahead and carry 4 decimal places for right now. So the slope length here is 8.2462. And that makes sense that our hypotenuse would be just a little bit bigger than our side there. Now, what is the IMA of this wedge? Well, if you recall, IMA equals DE over DR. So, although that's not really the one that we're going to use, if you remember going through the project Lead the Way worksheets and PowerPoints, you'll recall that for the IMA of a wedge, that's going to be the length, which is the length that's perpendicular to the height, divided by the height. Now, this too is going to be kind of complicated, because first off, the length is perpendicular to the height. Well, side C, that's our slope. It's definitely not perpendicular to either one of these legs of the triangle. We're still a little confused. Okay, which is the height? Is this the height, or is this the height? And is this the length, or is this the length? Well, The way Project Lead the Way looks at this, the height that we're talking about here is actually the height, or this overall part of the wedge. So the length is this dimension. So we've got 8 inches divided by 4 inches for an IMA of 2 on this wedge. Now, the AMA of the wedge is force times the resistance. We got to figure out a few things to determine what the AMA is. And we're given that the cutting edge of the wedge is 90% efficient. So we use that in our efficiency calculator to figure out what the AMA of the wedge is. So if we got an efficiency, that's E equals the AMA over the IMA divided, or times 100 is our efficiency. So let's go ahead and plug things back in. 90% when we divide out the 100, 90% becomes 0.90 times the IMA, which is 2, and that equals our AMA. Advantage here is actually equal to 1.8. So we have an AMA of 1.8 and a IMA of 2. How much resistance does the log provide against the cutting action of the wedge? Okay, so here now we need to decide, do we take and use the AMA, our actual mechanical advantage, or do we take and use our ideal mechanical advantage? Well, obviously you need to use the actual mechanical advantage to do this particular problem. So again, we'll set up a formula for AMA equals free of the force of the resistance divided by the force of the effort. Going back up to our force, we're told the effort force is 500 pounds. So let's plug and chug here. We got an AMA of 1.8 equals the force of the resistance is R. Our effort force is 500 pounds. We real simply do the calculation here. The resistance force equals 1.8 times 500 pounds. So I'll get my calculator out. Haven't been a long day to do that one in my head. So 1.8 times 500, and we end up with the resistance force here of 900 pounds. And it makes sense. We would have a lot greater resistance force there in the wood, and we want to decrease that resistance force with our effort force of the wedge. So that's how we would get that. Now let's just see what would happen if we go the other route here, if this is what they mean. And we can do some deductive reason here. If this is what they actually mean, our IMA here is actually going to be 4 over 2, or 1/2. So, and our AMA in this case then would become, as far as replugging in our efficiency, would be AMA of 90%, or 0.9 equals AMA over the IMA of 0.5. Our AMA in this scenario is 0.5 times 0.9, which equals 0.9 times 0.5, that equals 0.45 is our actual mechanical advantage here. We're not even up to 1. We've got a mechanical advantage, a very small mechanical advantage. So now let's plug that back in and say 0.45 equals our resistance force divided by the effort force of 500 pounds. So our resistance force in this case is 0.45 times 500 pounds times 500 pounds, which actually equals a resistance force of 225 pounds. Very small resistance force. So that means using this particular wedge and using 500 pounds of effort force, it's going to take us a lot greater effort force here than we'll will to go through that log. Well, in reality, you're most always going to have, when we're talking about these mechanical advantages, we definitely want to try to use less effort force. So that's why I think that the shape of the wedge that they are looking for is this one, because force that we use is going to be a lot less than the resistance force, and we would gain that type of mechanical advantage. If we got a less resistance, which means this, what this force of resistance here means is that it's a very low resistance to cut through that wood, and we have to put less effort into cutting the wood. The wood is a lot easier to split. The forces of the wood itself. So probably not the case in real life. That's why I say this is actually the answer. Most likely, to split that piece of wood, we probably need about 900 pounds of force to cut that in half, and we would need this wedge to decrease our effort in order to split that log in half. So there again, this is how we solve the wedge problems. This is one example. Keep working some of the other ones so that you get a good idea of how to set these up on paper and get them taken care of. Thanks for watching.